Let's now use our microscopic entropy equation to analyze a different situation. In this case, we're going to be looking at the reversible adiabatic expansion of a gas, right? So where we're expanding a gas and no heat is allowed to leave the system. If you remember from when we previously covered this example, right, we know that once again, from the mass balance, the initial amount of molecules is equal to the final amount of molecules, which is equal to n. In this case, since no heat is allowed to leave the system, during this expansion, the temperature is going to change. So if temperature is changing for an ideal gas, that means that the internal energies are not going to be equal. And of course, because it's expanding, the volumes are not equal as well. Okay. All right, and so if we plug into our molecular model to get S2 and S1, and we subtracted them to get delta S, we would get sort of the same thing that we saw last time, or we would get the same thing that we saw last time, where we have the equation kind of reduces down to this. Okay? All right, so I'm going to call this equation 2. Right, and this is, this is a true statement. But to gain a little bit more insight, about what this equation means, I'm going to apply two things that we've seen so far in regular thermodynamics. So to equation 2, let's apply two things from classical thermo. Or, classical thermo. Okay? All right, the first thing I'm going to apply is I'm going to relate the internal energies to the heat capacity, the constant volume heat capacity. Right? So internal energy is equal to N CV Ti. Okay? All right, and so, we've invoked this relationship before, and in fact, in chapter 6, we're just going to derive it more rigorously straight out. In any case, we're going to use this sort of relationship. And the other thing we're going to talk about, or we're going to use, is the fact that this is an adiabatic system, right? And we know for adiabatic systems that delta S is 0. Adiabatic systems are isentropic. Okay? All right, and so that's just straight from chapter 4. Right, so we're going to use those two things and apply them to equation 2. So we get delta S is equal to 0. So that's going to be equal to NKB, natural log of V2 over V1. Right? And for the internal energies, we're just going to apply the heat capacity formula. So CV T2 over N CV T1, all that raised to 3/2. Okay. All right, N and CV, those are constants, those cancel out. Okay. And of course, we have this is equal to 0. And so what we could do is divide out the NKB. And so what we get is 0 is equal to the natural log of V2 over V1, T2 over T1. And we could just do some algebra, right? We could take the exponential of both sides and then multiply this part out to the other side. And what we get is that T2 over T1 is equal to V2 over V1 raised to the negative 2/3. Let me move this down to make it a little bit more prominent. Okay. All right. And so this result that we got kind of looks familiar, though it's not exactly what we've seen before. So if you remember from when we looked at the adiabatic expansion in chapter 3, the result we get in the end is that T2 over T1 is equal to V2 over V1 raised to that 1 minus gamma, where gamma was Cp over Cv. Or we could even define it just like as V2 over V1 raised to the negative R over Cv. Okay? Alright, and so from classical thermodynamics, in our exponent we get negative R over Cv. For our ideal gas monatomic model, we get negative 2/3, right? So why is there a discrepancy here? Well, it's actually not a discrepancy. These are actually the same result, but this one is specifically for a monatomic molecule. Okay? And that's because, coincidentally, if you took the heat capacity of a monatomic molecule and divided it by R, what you would get, or the constant volume heat capacity specifically, what you would get is 3/2. Okay? And in fact, I encourage you to go look up the constant volume heat capacity for argon, and then just divide that number by R. What you will get is exactly 1.5. Right? And so this result is actually the same as this result as well. Okay? So microscopic in general, this microscopic S gets us the same result as classical thermodynamics.